Okay, I'm going to get started. So Tuesday we talked about authentication. Since the vulnerability class is broken authentication and session management, I'm going to talk a little bit about session management, and then I'll talk about the ways both of these things have been exploited. So what is session management? This is after you authenticate with a service. Session management is sort of an embodiment of your authentication state throughout the rest of your interaction with the website. And we talked about cookies. That's basically a session management mechanism for you to, validate to the server all the time on these requests that you are you are a particular person. So sessions in general maintain this typically authentication state, but some of these sessions can also talk about your authorization state. And this is done because HTTP is typically stateless. It's a stateless protocol. And so this can be done, implemented in a variety of ways. We have talked about two ways already. When we talked about the web basics, we went through a couple of these things. The first mechanism was via the HTTP cookie header. And within this header, there is developing a more or less a standard way of carrying sessions. And that is through session IDs. So in PHP, if you use a framework, you'll get this PHP session ID that gets passed through the cookie field. And then an equivalent in Java is the JSession ID. Okay. The other way we talked about this was with the HTTP authorization header. So we talked about basic authentication in HTTP. When you are accessing a protected resource on the server will require you to supply credentials, and it will send in the response header this www-authenticate header. It challenges you, hey, supply a username and password, and then the user types in the username and password, and then sends in the subsequent request a request header called authorization, labels this as a basic auth attempt, and then what's in the payload is a base64 encoded username password field that is attached. And then the server will decode it, check the credentials, and allow that access. Okay, so this is just review. One of the things that you can see with basic auth is that if you look at what's happening in basic auth, this authorization credential is sent on every request that needs to be validated. And you can see that basically the authorization and the authentication is sent at the same time. Like you're resending your authentication credentials every single request. And typically this is poor form. Like you should not be sending credentials or checking them over and over again. So that's a drawback with this approach. Something that you'll come across with, especially if you're doing cloud computing, is a thing called an OAuth token. So if you are accessing web APIs, you'll typically be using these tokens. If you have, there's this term called federated identity management. Well, what is that? Well, if you have ever done social sign-on, where you say log in with Google, log in with Facebook, these sorts of things, that's what this is. And it's done using a protocol called OAuth. And with OAuth, your embodiment of your identity to that third party is encoded in a token and then carried over HTTP. Okay, so that's what an OAuth token is. And the way this works is that the identity provider, like the Facebook or the Google, they have a private key, public key pair, and they're trying to sign off on the fact that you had validated with them. And this token that gets generated is an embodiment of them vouching for you, so that when you subsequently access a third party, the third party can check that yes, you had been blessed. It's similar to TLS if you think about how it's set up in terms of, hey, I trust this person to sign off for me, and then I'm going to use that and your knowledge of that person's public key to transfer that trust. Okay, so that's what an OAuth token is at a high level. The way this is carried is through an HTTP, again, same header, the authorization header. If you can see it, it's kind of small. Actually, maybe I'll dim the lights because. So it uses the same authorization request header as the basic auth does, but it uses this keyword bearer. It's called a bearer token. And so after the bearer, you'll get the actual access token that will validate your access to that third site. Okay, so here's an example of it being carried. Here's a post request on an update. And this is, for example, so you have an API that is being protected. And then as part of the authorization to that API, you supply this bearer token. And that allows this host to validate that you have a particular identity. Okay. So one of the things with OAuth tokens is that it can be sent across multiple mechanisms. So you could use the HTTP authorization request header, or you could actually include it in the post body for token transmission. So here is a similar request, but the access token is explicitly added as a form field submission. Okay, another thing that you might see are JSON web tokens for authentication. And this is an extension to OAuth tokens. But what JSON web tokens attempts to do is it's trying to support data exchange. So if you're sending specific data, authenticated data back and forth between the two endpoints, that's what this token format supports. And then also authorization assertions. Like not only do I want to validate an identity, but I want to validate the authorization state of that identity. So a little bit of access control rolled into the identity stuff. There are other options for implementing sessions that you might see. HTML5 session storage is a way to get state shared between client and server. We'll talk about hidden form fields. Some of you have gone full into the hidden form field, the CSRF protection. That where, as part of your interaction with a web form, they send you this token as a hidden form field, and you have to present that token back, which is basically a session to actually access the site. Okay, so now we're going to talk about all the ways that authentication and session management can be broken, and this is the, I guess, number 2 in the top 10 OAuth vulnerabilities. So I'm going to start with an example. Once upon a time, in a place very nearby, and you can see from the sender of this email address, there was this fund drive that happened, and this is a great thing. You want to support this fund drive. So yeah, if you have your charity, use your payroll to sort of fund a charity of your choice, pre-tax, and then everything is good. If you looked at this email and you read it all the way down, you could find a way to sign up for this thing. And read this very carefully and see if there are any problems with this email or with this mechanism, if you can read that. Is there a problem, first of all? This went out to everybody. And apparently only a handful of us complained. Yes?
You're giving away private information like your ID number is associated, right?
Yeah, so if your ID number, if your ID number is known, my ID number is known by a lot of people. Anytime I sign a form, and one of those, what are the yellow sheet, whatever the registration forms are, I put my number in there everywhere. So if that ID number is known, then what can that person do to me?
You can sign anyone up for a charity.
Yep, you can sign me up to any charity of your choice, not mine. And then that would be a payroll deduction off of me without my authorization. Okay, so this was only a couple years ago. So this happens when you're designing things. That's one of the issues. So we're going to cover a bunch of these different things. There's a lot of there's a lot of ways this can go wrong, and I'm not pointing fingers because this stuff's hard to get right. But these are the kinds of things that we're going to cover throughout this section. What you saw earlier was guessable default credentials, right? Not only that, it wasn't that. I mean, so if you knew that information out of me, then you didn't even have to guess. You knew my default credentials immediately. And so this is really playing out when we talk about the Internet of Things. All of these devices, when they're shipped, are shipping with default username and passwords because it's hard to manufacture things with custom usernames and passwords for each individual device, right? Like, especially for instructions, right? Like, you know, how am I going to print out a new set of instructions for every single item that I'm going to ship to a user on the other side? So this is everywhere when you're talking about Internet of Things devices. And so, moreover, the problem is exacerbated by the fact that almost all of these devices don't force the end user to change the default credential. And so this is the statistic where pretty much, we have a lot of devices out there with default passwords. And of course, you can create a huge database of default passwords. And if you have forgotten yours, you can do a factory reset and then go back to the default passwords of any device that's out there. Okay, and this leads to, and this was from last week, a hacker, a very industrious hacker, who found 500,000 devices that were connected to the internet and basically discovered their usernames and passwords and then published them. So now any of us can have access to 500,000 of these devices, which is a problem. And so if the way this person revealed these things was to scan everything for the factory set default, or just use the easy to guess passwords from the previous class. And that was enough to get 500,000 of these things. Okay. Another problem is vulnerable account and password recovery. So if you are sending guessable password reset questions that people can answer legitimately to your victim, as your victim, then you can actually pretend that you are that victim and you've lost your password, and then be able to recover a new password for yourself or, to attack the victim. So this was Sarah Palin's route to compromise in 2008. Back then, Yahoo had the zip code, the birth date, and where she met her spouse as the security questions. And those three things are easily guessable for a public figure like she was. So that, I don't think they do that anymore. They got other problems. Yahoo has other problems with their authentication now. That's not one of them. There's also a similar guessable change my password links, right? Like if I say, if you've forgotten your password and I haven't stored your password, I'll send you a magic URL that when you click, it'll just say, okay, set your password to this, that, and the other. If that link is produced in a way that an adversary can guess what that is, then the adversary can basically click on that and change your password directly, as you would if you have lost it. Resets that are sent insecurely. So this happened, this is last year. No, yeah, this is last summer. So the 7-Eleven customers within their app, so a lot of, it's similar to like Starbucks where you have a bunch of money in your app. So these customers lost $500,000, and it was because of the mobile app was implementing password resets in a way that supplied an additional field that allowed the hacker, or anybody actually, you didn't have to be a hacker, to request that the password reset link be sent to a third-party email address. Typically, when you say, I forgot my password, click on this to reset it, it will send an email to the registered account, right? But if maybe, I don't know why you would put this form field, but they allowed you to set the email where that password link was sent to, and you could set your own. And that's what and this is $500,000 from this app, okay? And so, yeah, what I like, you read this, it's like, yeah, no need to run burp or Postman. This is way easier hacking than what unfortunately you guys, you're being forced to do. Okay, vulnerable authentication processes. So there are no rate limits on the authentication attempts and failures. So when you're brute forcing passwords, typically you would like that server to be like, whoa, you're basically brute forcing my accounts. I'm going to shut you off. You have to implement that on the web server, right? Otherwise, someone can basically scan your usernames and passwords of your accounts directly. So not only on the web front-end login, you have to make sure on all your APIs that you are rate controlling the authenticated access. And especially with 2FA. So this was an example last summer again, that you can't just throw up 2FA and not check someone brute forcing 2FA codes, right? Because typically 2FA, well, before they were like 4 digits, but even 6-digit 2FA codes. If I can brute force 1 million 2FA codes, well then if it's a 6-digit code, I win, right? And so you need to rate limit any submission with 2FA. Like so with that Google Authenticator app, like you have to make sure they can't send in 999,000 2FA codes against that one account. And apparently, Instagram didn't do that last summer. And so if you look at this article, it was possible to brute force their 6-digit 2FA code using cloud computing. So this is what the cloud has wrought. This person set up 5,000 IP addresses, so 5,000 virtual machines. And this is rent a virtual machine, right? Like you're only using it for a very short time to get an IP address. And it cost this person an estimated $150 to brute force a 2FA code on a single account because Instagram wasn't blacklisting IP addresses. And so what it needed to have done is as soon as you got like maybe a dozen incorrect guesses from a single IP address, you should completely shut that down, right? You shouldn't take 5,000 times, well, I guess if they did this with 1 million, that would have been like 100, like, well, maybe not 100, 50 or so. So per IP address. So this happened. Another issue is with CAPTCHA. So here's an implementation. So anytime you have authentication workflows, you can have logic flaws in these workflows. So here's an example of a CAPTCHA authentication workflow where it checks to see if there's a CAPTCHA. And if the CAPTCHA answer is valid, which is what this is checking, and if this is false, then the CAPTCHA is invalid and you redirect the flow. But if this thing isn't true, then the CAPTCHA is valid and you allow the authentication to happen. The problem with this workflow, if you haven't caught it, is that if there's no CAPTCHA provided, the script doesn't fail the login. So it doesn't fail safely. So what this needed to do is to immediately redirect if the CAPTCHA isn't supplied in this workflow. So that's a subtle bug. You have CAPTCHAs that have answers that are easily guessable. So there are CAPTCHAs out there that are like, oh, add these two numbers together, and they're both single-digit numbers. And that kind of CAPTCHA, all you need is like 20 requests to basically overcome that CAPTCHA. Repeated answers, and then CAPTCHAs that aren't properly resistant against optical character recognition. And then finally, there are CAPTCHA implementation errors. So there was a vulnerable workflow that I mentioned earlier in this class, where in PayPal, the response to the CAPTCHA validation ended up sending the user's login credentials in the clear across the authentication workflow. Okay. Other kinds of authentication issues, and these are related to your homeworks. One is side channel attacks in checking the credentials. So the username is checked before the password instead of simultaneously. We talked about that. There are attacks on the cryptography where you can use the fact that so runtime differences between valid passwords and invalid passwords can be used as a side channel to predict what the password characters are. And this is what program number 2 is going to do. You're going to have a authentication sequence where the characters of the password can reveal the correctness of a character or password is going to change the timing of the authentication. And then you're going to write a program to automatically exploit that. Another one are case sensitivity issues. If the database and the web application handle the case of the usernames differently, then you can create a user with an existing username by changing the capitalization. And this is an exercise in your homework, in your lab, the Web for Pen Tester lab. Okay, so an example is if someone creates an admin account with capital A, they'll be able to access the account of admin with a little a. So that actually is exactly what you're going to be doing in your lab. Okay, another set of issues are password storage problems. The first issue is that a site that stores passwords in the clear instead of hashed. So if you have and this is an example of a password file that's stored on the server, so this is the worst kind of way to store a password, where you see the user ID, the user's name, and then the password, and of course these two users are using the same password, and it is called password. And in this case, a single compromise of this site will give up all the user credentials. And then we have already talked about credential reuse, allowing that thing to be sprayed everywhere and harvested everywhere. And so Facebook ran into this last year, storing hundreds of millions of passwords in plain text. This wasn't accessible publicly, but like if someone had compromised their site, they would have been able to access this, so hopefully they didn't get compromised. So typically what you would do is hash your password with what's known as a salt. If you don't hash your password without a salt, then you have the thing in the clear, as you saw before. So typically you would hash the password, but if you just hash the password and you hash it without a salt, then what a salt is this random data that's hashed with your password to generate your hash. Okay, so in the picture that we have here, the password is just hashed with a hash function. So if you send the password to a hash function directly, then what happens, you have these two users, Charlie and Duck, that had password as their password. If you're just going to send that to a hash function, you look at the hashes that Charlie and Duck have, and you see they have the exact same password hash. So what this means is that if you break one account, you automatically know the second account's password. And so you can brute force attack, you could do a dictionary attack on Charlie, and as soon as you find the word that generates Charlie's hash, you know exactly that Duck has the same password. So the way to address this is to store the hash, or to do the hash with some random number, and that random number is different per user. Okay, so that's what a salt is in cryptography. And so there are sites, these rainbow table sites, that have created hashes, SHA-1 hashes and MD5 hashes of all the popular words. And so you can actually take a hash that looks like this, 5E88, and look up that hash on this site, and it'll do a database lookup to find the plain text. So you don't even have to do a dictionary search. And so if you are using a password scheme that's not salted, you should probably switch over to a salted version of this. Okay, so that's that one. So typically, you add a random salt to every user's password entry, and then you would store, instead of the hash without the salt, you would store the hash that's with the salt, and then these two users have different hashes. They have different salts, different hashes. Okay. So now the adversary, even though Charlie and Duck have the same password, the adversary has to brute force both of those. Yeah.
Do you generally store the salts in the same file?
Typically they're stored in the same file. Because when you validate the hash, like the password scheme has to pull it out and do that, yeah. Okay, another issue is that cryptographic hashes are used instead of password hashes. So cryptographic hashes are intended to be fast. So if you need a file signature, that hash function should go one pass through that data and generate a hash result. And for what they're trying to do, message integrity, that's a reasonable thing to want to make fast. But the problem here is that if someone has used a dictionary word as their password, it's easy enough to run a cryptographic hash on every single word of the dictionary and have it be done in less than a second, right? That's like what? How many? Like if it's like 20,000 words in a typical dictionary, then even with this salt, you know, being able to do that on this is pretty trivial, right? So what you want to do, and this is the state of the art, is to employ a password hash. And what a password hashing algorithm does is it employs what's known as hash stretching in order to repeatedly run the hash function multiple times to generate the actual result. And this is making the hash function intentionally slow, so that if you're going to run the hash algorithm and do a brute force attack, it's going to take you forever, but it won't be so bad to run the hash algorithm against one entry a single time. So that's the idea of a password hash. And so the attacker obtaining the password file can't perform an efficient offline dictionary attack in order to break the password. So if you have a compromise of this file, and it's got the salt and it's got the hash, the fact that the password stretching algorithm says run this hash 10,000 times on the password before comparing the result, the fact that this is being done 10,000 times slows down the adversary to make this a much harder cracking operation than if this was just a cryptographic hash. And this is what scrypt and bcrypt, these algorithms will do. Each iteration will cost you about 100 milliseconds, and you can also, on some of these algorithms, you can actually specify the number of iterations you want that scheme to do. And so in this case, if you really want to make it painful for an adversary, you could say 140,000 times, and then that hash, and this is a hash chain, so the output of the one iteration feeds into the next one, so you have to run all 140,000 to actually emit the hash. Okay, and so when this is almost done right, this is good. So like if you have a data breach, like Under Armour got it mostly right. They were actually using bcrypt, but the way they implemented bcrypt was because they had existing users. When existing users came back onto Under Armour's site, that's when they would prompt for a change in password. Because you don't have the actual password stored, right? Like you only have the old hash, and so they don't know what the password is. So they can't generate the bcrypt version of the hash with an old SHA-1 hash. And so what they were doing was any new logins for users that had an old SHA-1 hash in their database, they would then force them to re-authenticate with their password and then use their password with scrypt or bcrypt. The problem is that when they got compromised, there was like a huge segment of their user base that hadn't done that hadn't logged back in again. And so when they got exposed, they had to go back, and all the people who hadn't logged in before, they had to notify that yes, there had been a breach. And this is actually lost dollars for Under Armour because of the sort of the law, the way we have our laws set up for data breaches. Flipboard also almost got it right. So this was over the summer. And so the vast majority of their passwords were hashed with bcrypt, but they still had some that were SHA-1. So SHA-1 is a cryptographic hash that's super fast, and then you should be using bcrypt if you have if you've implemented that. And then Quora 2 years ago had exposed 100 million passwords, but people didn't really care that much because they did pretty much everything right. The first thing was, and this is in the article, and so people were like, yeah, they got breached, but they did this. First of all, they were storing hashes, so good for them. They were using bcrypt, so using bcrypt makes it so that the adversary has to wait for their great-great-great-great-grandchildren to be grown up before they can get a good number of passwords. And then the third thing, they were salting the stored hashes. So when they did this analysis, they were like, okay, they at least got their password hygiene correct on this one. Okay, so they got the gold star, at least for the password storage part of the operation. I don't think I checked back to figure out how they got breached, so they probably got something else going on that got them breached. Probably one of the other top 10 vulnerabilities. Okay, are there any questions about password storage? So now if you go out in the real world, you'll know there's actually a link. I think if you go to this link, this is from 2012. This is pretty much this is from 2012, but we're still here in 2020 talking about it. But pretty much this link has everything you need to do for storing passwords that you would want. Okay, another issue is vulnerable session IDs and tokens. One problem is having session IDs that are carried in things like URLs. You should never do this. And the reason why you shouldn't do this, here's a scenario. You have a user of your site browsing your web pages, and then as part of the authentication, sends the credentials. And if you are embodying the user's authentication state in a session ID, if you send via URL rewriting, if you send that session ID as part of the URL, so here you see this bank site has the JSession ID as part of the URL. If your user goes and visits some other site, sort of like hacker.com, as part of the interaction, if the user goes to this site from this page, then the hacker can basically look at referrer logs and then see that the URL that referred that user to this site has a particular session ID. And so you can pull the JSession ID out of the URL, the referrer URL, and then hijack the session, if that's the only thing that's being used as the authorization state. Okay? So that's a problem. You also have a problem where any token that you send in cookies must be done using the secure flag in over HTTPS. You should not be sending any cookie information over clear text HTTP. Now, we've been pretty good about making sure everything goes over HTTPS, but it's this flag, this secure flag in the cookie header that really prevents the browser from revealing a session token effectively. Back in the day when we didn't have this, there was this tool called Firesheep, and this is a screenshot of Firesheep, where you could go into a cafe and an open wireless network, and you can watch for cookies going by. And if you can see here, like Google cookies, Facebook, Twitter, and Flickr cookies are going by, you could basically dump the cookies that are over the wire and pretend to be these people over the network. So fortunately, most social media sites have the secure flag set on their cookies, and you can't hijack someone's session cookie. So this picture doesn't work anymore, but that's what used to have happen. We used to have happen. Okay, Another vulnerability is repeated or unchanging session tokens that are not bound to an IP address. So if you can get access to these tokens, you have persistent access to that person's account on that site. So here's one from last month, the $20,000 cookie. And this was a breach of HackerOne, ironically. And so what happened here is that there was a interaction between someone at HackerOne and a sort of a community member of HackerOne. HackerOne is a community of sort of bug bounty folks trying to get bugs off of sites. And so as part of technical support interaction with this community member, the company analyst sent a curl command that actually included a valid session cookie. So in their video call or session, whatever session they were using, there was a curl command exchange and a session cookie was in there. And so the problem is that this cookie wasn't being changed. And so by revealing this, it allowed that member full-on access to anything that analyst had on the HackerOne systems. So this person reported it, and HackerOne issued a $20,000 bounty to this person. Okay. So one of the things that this thing reveals is that, when you issue a session token, you should probably bind it to an IP address. So if that cookie was only valid for a particular IP address, then the community member would have presented an invalid cookie to HackerOne. Okay, another issue are unsigned tokens containing semantic values. So if you are using a token format that has sort of privilege levels encoded in your format, then and that thing is not digitally signed, so you have semantic information that doesn't require a signature by the server, the client can just tamper with that cookie directly and elevate privileges. Okay, so that's an issue that you're going to have in one of your labs. And this is an issue that happened with these JSON web tokens as well. Another issue is predictable session tokens. So if, for example, the server is issuing session tokens sequentially, then you can take your session token number, guess the next couple of them, and then take on the identity of subsequent logins. So that's another issue. And this can lead you to blind hijacking of sessions. The final one is insecure management of session information at the server. So typically, on the back end, you want all of the individual user sessions to be stored securely. If you have a site that's vulnerable to command injection or code injection, and the command that is injected can go to a directory like in PHP, there's a shared session directory that if you go into this, all the session IDs and all the session tokens of every single user authenticated onto that PHP site is stored there. If you can inject a command that dumps that directory content, then you have you can log in as everyone on that site effectively. And this is an example in one of the pen tester labs where you can hijack other sessions by accessing the session information on the server end. Okay. So some prevention. Lock down all your passwords, so removing unnecessary accounts and default credentials. Having a password policy that enforces a minimum length of greater than 8, or passphrases if you are using passwords. On the server side, people are doing this more often. They are checking any new passwords against those that appear in breaches and saying, no, you can't have that password. So that's in terms of hygiene, something that people are putting in their sites more often. Not allowing dictionary words or usernames and passwords. Those are also being done, but obviously if you're doing passphrases, then those are meant to be dictionary words. So maybe you can allow dictionary words if the password is like 20 characters long. because then you know someone is using the passphrase strategy, and then you're using the length of that. The fact that you have a much longer password allows you to then maybe allow dictionary words, is the idea. This is a hard one. Immediately invalidating all passwords stored with an improper hash, the cryptographic hash. So if you were Under Armour, maybe you would have just invalidated all the SHA-1 passwords up front and deleted those hashes, and then forced an account recovery on anybody who hadn't logged in by the time the bcrypt was deployed. Yeah. Well, the idea is you would delete all the SHA-1 hashes, and then when someone tried to log in again, you don't have a SHA-1 hash. You would have to do an account recovery on that person, rather than allowing that initial login and having that person change the password to do the bcrypt stuff. That would be the idea, but that's a pain point for a company because users don't like account recovery is costly on the user end as well. Changing your password is costly. But yeah, so they ended up delaying it, and then they got breached. Yeah.
If I do happen to capture someone's encrypted or secure cookie,
Mm-hmm.
and although I will not be able to see the passwords or usernames in plain text, but if I do resend the same secure cookie to the server, would I be able to see something?
Yeah, you're basic, because the embodiment of the identity of that user is in that cookie. So if you have that cookie and it's not bound to the IP address, and that's the HackerOne issue. They found that cookie. The cookie wasn't being changed often enough. So that's another thing, is if you are changing that cookie every 15 minutes by doing some kind of reauth or chaining the credentials, somehow rotating the cookie value, then that thing would have expired, and then yeah, revealing it wouldn't have been an issue. But typically, and this is why when we get to cross-site scripting, they're trying to get at your cookie, because that cookie is basically your identity to that other site that you're trying to pretend to be that victim on. Yeah.
Sometimes in a particular place or in a room, multiple customers have the same IP address.
Yeah, in the same room. So if you are in a room, everyone's got the same IP address. If you're using a NAT, so like in your home network, then yes. If you have a cookie bound to the IP address and someone in your house has hijacked your session, maybe your kid wants to, delete parental controls or something like that, then yes, it's bound to. Yeah, so it depends on you. You could implement this in a variety of architectures. Some people don't want to bind an IP address to the cookie, because if you think about your mobile device, you could be switching from Wi-Fi to 4G or 5G, and you don't want to have to reauth, right? So whether or not you bind the cookie to an IP address, that might be a business, like a user interface decision as well. So you trade off usability for security, which is a trade-off a lot of people make.
So binding to the MAC address of the device after asking permission, that would be different.
Binding it to the MAC address of the device is a problem, because on the server you don't have the client MAC. So the way networking works, the MAC device, the MAC is a hardware address that's sent hop to hop. That information is completely lost on the server. Never gets to see the client's MAC address. If it did, we'd have a privacy problem. Like, that would be a boon on all the people tracking you, right? Like, if you supplied your MAC address on all the requests that you make to the server, then people could, you could be surveilled. They get your MAC address and then send it in a cookie.
And even if you delete the session or or even a logout, still when you log in with some another ID, they are able to see that again. It's the same person.
Okay, so when you log out and the site still knows that you are still logged in, that could be a MAC thing, but there's also there's different kinds of cookies, and maybe I should cover this in this class. There are different levels of cookies for a site. There are some cookies that are just meant to identify you, which even when you click logout, doesn't go away. You have to actually wipe your browser of all the cookies for that site. There are other ones that are for really sensitive functions on that site. These kinds of higher level authorization cookies have a much shorter timeline, and they force a reauth in order for you to get one of these things. So maybe like a 5-minute window, you have this authorization cookie that allows you to transfer money on the bank. But when you log out, it'll kill maybe that cookie, but it won't kill the other cookie that's just tracking who you are so that you can get your personalized information. So that like Facebook would never want you to completely log out of their site if they're using a tracking cookie. You basically would have to delete the cookies completely, all the cookies. And so typically in a cookie you'll have multiple fields, and there should be at least one that's tracking you for these sites. I go here and then here. Yep. You have a question? Okay, so the question is, can Under Armour brute force to do a dictionary attack against all of those users that still had SHA-1 hashes to find their passwords and then use those passwords to generate the bcrypt versions? Yes, they could have. In theory. In theory, they could have done that, and then migrated at least the people with the really easy passwords over to the more secure ones. That's interesting. I have never heard of that happening, but if someone has come across it, I'd be interested in including that. Yes.
Are there any session authentication systems that like involve the trusted platform module or other like hardware?
Is there any authentication that uses the trusted platform? I don't think it's embodied in the session cookie per se. The trusted platforms are being used in the operation of other things, like so for the YubiKey, for example. But I have not heard of like using the YubiKey, for example, to inject something in the session token that allows the other side to continue. Yeah. I don't know of one, but again, if someone comes across something that looks like that, I'd be very interested in seeing that. Okay, the other thing to do is, because adversaries are continually targeting users for their credentials, this is something that some organizations are doing, not these two particular ones, but there's a cottage industry of software developers that have built products to help enterprises figure out who their most vulnerable users are. Like, which users in your enterprise are most likely to click on that phishing link? And so as part of this, you want to be able to train all of the people in your enterprise against targeted phishing attacks. And the folks with the least amount of training are getting targeted the most. So the folks in the HR departments, the folks in legal, the folks in the executive team, they have the least amount of technical training, they're getting attacked the most. There's this podcast on Risky Business called Very Attacked People, and this is the kind of training that if you want to secure the enterprise, it's not like, I mean, patching helps, but like going after and securing the people involved in an enterprise is going to be even more helpful. You'll find that the attacks on the people have generated a lot more revenue for a hacker than exploitation of like a web server, unfortunately for us. Okay, and then from last class, implement multi-factor. And to use appropriate threat analytics. So again, this is within the last year or two, the idea of threat analytics for your employees, to authenticate your employees into the enterprise. This is something that a lot of companies are releasing products that into the enterprise for. So IP address, geographic location information. There was a company, I think it's Cylance, has got this thing called Persona, where they're using machine learning based on a particular user's profile. So your access to the company resources is sort of being learned underneath, and then they're using that, like the deviation from that learned profile, using whatever ML model they're using, deviations from that is being fed into a threat analytic thing to force a more strict authentication if there's something suspicious going on. Okay. The out-of-band token is also, so either the push notification, the text message, or the YubiKey, that's what that refers to. And one caveat is to beware of single-factor hiding in multi-factor close. So here's an example where a T-Mobile employee hijacked someone's Instagram account using a single factor, even though they had two-factor turned on. And the way this worked was you just did a SIM swap, and you did a SIM swap, and then you forced Instagram into a account recovery workflow. And as it turns out, the account recovery workflow only required ownership of the mobile the mobile phone number, right? So if your account recovery only requires access to a phone, then even though your regular login is 2FA'd, the person can hijack your account using the recovery mechanism. So this employee did a SIM swap, knew the phone number of the Instagram user that they were targeting, because it had it was like a juicy Instagram handle, like one of the short ones that got like a cool name. And so like if you know the phone number of the person you're going to target, then as an employee you have access to phone numbers. You would just do a SIM swap, tell Instagram that you lost your password. It would send the reset link just to the phone, and then you can just set up the account with a new password. Okay. Yes, question? That's a hard problem, isn't it? Yeah, if you lose one of the factors, and in the account recovery, you have to do two factors, that automatically implies you have three factors, right? So that's a good question. I mean, for Instagram, it would be, so if you would need access to the email address, would be, like, so I think the problem here is that password reset link, yeah, I don't know how they actually address this. But yeah, in that password reset for the phone, you would need that third, the email address, probably, ownership of an email address as part of a recovery process. Or a phone call. Like sometimes, like for Google account recovery, the really slow way of recovering your account involves contacting technical support over the phone on that one. And then if you're doing multi-factor, make sure it's secure. And so a lot of these banks had been using text messages as their second factor. And as it turns out, they weren't considering the fact that adversaries can spoof cell towers and that they can do the phone porting to hijack the phone number on that second factor. And so there are accounts where, like, if you have a high-value target, you're going to go through those steps in order to hijack that second factor, and adversaries are doing that. So this is just an example of emptying a bank account using two-factor. Okay, verifying your entire authentication architecture, so making sure all the credential transmissions are encrypted using TLS and SSL. So in particular, the form submissions for the passwords. Limiting the exposure of credentials, so don't send the credentials repeatedly. Making sure you're storing the credentials appropriately at the endpoint, so that refers to the password hashing stuff as well. And then making sure your account recovery process is secure. And then enforcing a lockout policy if someone has tried too many times on your authentication. Verify the session management architecture. So don't roll your own session management. Use the framework's session management, which has been vetted, hopefully. Keep as much information on the server as possible. And so don't put any semantic information in the cookies if you can avoid it. We'll talk about this a little bit when we talk about deserialization attacks. Sometimes you're forced to have the client store semantic information, but if at all possible, you want that session ID to be just a random number, to have nothing that the client can tamper with, like an authorization level. Like you won't say, role is equal to user. You don't want that in the cookie, because then you can just say role is equal to admin and then get admin access. So that's the idea there. Bind the cookie to either an IP address or a specific set of paths, so that if the cookie has been hijacked, you have done least privileges on that cookie, is the idea. You've targeted that cookie, and this is for the hacker one. Like if that cookie didn't embody that particular analyst's entire access, then the revelation of that cookie wouldn't have been so damaging. So if you have cookies that are bound to specific parts of your infrastructure, that will limit the damage of an exposed cookie. Never trust the client or the network, so encrypt and digitally sign those session IDs. Or if you are sending semantic information for the client to store, digitally sign that, so that when if the client tampers with it and sends it back, you know that the tampering has happened. And this is the key problem with deserialization attacks that we'll talk about in 2 weeks. Okay, removing the session information from the URL and the browsing history is another thing there. Timing out those sessions, so making sure not only the session IDs but the tokens themselves continually expire. That would have helped in the HackerOne one. And then verifying that when someone does click log off, that it actually destroys all the session information, all the sensitive cookies and tokens. There are cases where the logout button didn't actually do anything on the server end, but I don't have the actual article that talks about that vulnerability. But there are tools that you can. So as part of software, software assurance on your site, there are tools you can run against your site that automatically reveal whether or not you have these issues. Okay, and then likewise with the authentication stuff, with session information, you want to make sure those are protected by HTTPS, and for that you would need the secure flag, and when we talk about cross-site scripting, you would want the HTTP only flag on these cookies. So I'll talk about that next week. Okay. So the second thing I want to talk about is unvalidated redirects and forwards. This is the other vulnerability. So what is an unvalidated redirect? This is an exploit where an attacker sends a link to a victim via email. So here's something from Internal Revenue. So you probably have seen these emails. I mean, I've gotten enough of these things. And as part of the attack, there is a link. And if you look at the link looks totally legit, right? It's got HTTPS irs.gov. It's got a tax refund route that actually is a legitimate route. And it says, okay, claim your reward. If you look very closely at the very end of the URL, there is some parameter that says destination is equal to an evilsite.com. It might be even obfuscated in a way that, if you're not looking very carefully at the entire URL, the URL could be pretty huge. So you could miss this URL parameter if it's off the screen. And so the idea is the victim gets this link, does a hover over the link, looks legitimate, clicks on that link. And what that link does is it's going to go to IRS. So that's what this link, so here's IRS on the right. And the request is sent to the vulnerable site. Now, as part of this vulnerable site, the adversary has figured out there's a part of the site that does a redirect. And what it does is it tells the user, using that location header in HTTP, it says like, oh, I don't do HTTP. I'm going to redirect you to the HTTPS version of the site. So that was like one of your Web for Pentester exercises. So if you have a site that uses redirection to bounce a user from one part of the site to another, then what happens is if it's vulnerable to attack, the IRS site will just redirect blindly this victim to whatever parameter has been supplied in a URL parameter. Okay? So that's the vulnerability. So this then redirects the user to the adversary's site. And then from here, the evil site can install malware or can phish the user, do this, that, or the other. Okay. So here's an example, a more realistic example. The user accesses a page that requires authentication. So I'm going to go to, I pick on Yahoo, and it's not intentional, but I just have these examples just because I know about them. I have a Yahoo account too. I'm not ashamed to say. But I do have a Yahoo account, so I go to mail.yahoo.com and I'm not authenticated. Now, the way the authentication architecture used to be implemented, the login part of Yahoo was separate from the mail part of Yahoo. And so what you would do is the mail site would then redirect you to the login site. And so you can see here, login.yahoo.com. But it wants to redirect you in a way that after you're done with the login site, you return back to the mail site. So this is a legitimate reason for doing this URL redirection, right? And so as part of my login flow, I have as a parameter this done field that says, when I am done logging in, send me back to mail.yahoo.com. Okay. And then after login, you would go back to the origin page. So this is what an adversary might do. The adversary might, so the issue here is that if this login site takes this thing and does a redirection, the redirection has to be validated. If you don't validate the destination and you send the location header that points to some evil site, then you could be, Yahoo could be redirecting you to that evil site directly. Okay, so you want to avoid that. So this is, so here is a site with an unvalidated redirect vulnerability. So if you send a request to r.yahoo.com, it will redirect you to what URL parameter says to redirect you to. And so what an adversary would do is find this redirect that's vulnerable, screen scrape Yahoo's login page. So get all the assets, and then put up a site, loginyahoo.com.cxx. Make sure you get the SSL certificate to make it look really legit. And then you phish a user with a rogue URL in an email or a website, and when the user hovers over this link, the user sees the redirect.yahoo.com. That is a legitimate site. And then somewhere in the parameters, you see .done is equal to this rogue site, loginyahoo.com.cxx. So the victim actually sees something that has the right domain. That's the important thing, but ends up at a site that looks like Yahoo, the login thing, but is actually controlled by the adversary. And this is where the adversary can say username, password, and then you get the credentials. Okay? Okay, so maybe this was how Podesta got it, but these are really devious attacks. So you could see, like from a UI perspective, this is hard for even us to avoid at times. Okay. So you see this in code. So we're on the programming side of this. So anytime in code you see stuff like this where you send a redirect and that redirect is taken directly from a get parameter, that's vulnerable, right? Like you would get the parameter and then you would hopefully validate it is what you want to do. So here's a vulnerable Java pattern. Here's a vulnerable PHP one where you get it out of the URL parameters and then you immediately set the header, the location header, to the redirect URL without validation. So that's another error that's unvalidated. Here's a .NET version, and the .NET version is a little more verbose. But you see as the logon takes a string that has a return URL, and then before checking it, you redirect to that return URL, and that also will call the location header to redirect you somewhere else. Okay, the other part of this is unvalidated forwards, and this is similar to the redirects, but you're remaining on the exact same site. So a redirect puts you somewhere else, but the forward is going to send you to a different place on the site, And the idea of an unvalidated forward is that you find a place on that site that's sensitive, that you wouldn't have access to from the front door, and you can see if you can forward yourself to that route without having to authenticate. So it's basically the same attack, but done internally. Okay, so here's the animation, sees a link in a vulnerable site, and there's a page that calls the forward. And so in this case, the forwarding code assumes that this destination is set by the page itself, and will redirect you to an internal route using that parameter. And the code assumes that the adversary isn't going to be able to tamper with that part directly. And of course, this is a URL, so the URL parameter can be tampered with easily. So the attacker will inject a rogue parameter in the destination. And then because the application is written to automatically do the forward without validating the actual target. So in this case, you get the parameter dest, and then you immediately call the forward on that target. And this will then send you, if that target of the forward is some sensitive route on your website that you shouldn't have access to, then you can get unauthorized access to the site. Okay. Here's an example, Java server pages, where, again, getting the parameter, the forwarding parameter, and then blindly forwarding it in the response. That's the vulnerable pattern. Okay. This was number 10 in the OWASP top 10 in 2013. It fell off, but I figured this is such a short description that I would leave it in the class. Okay, so some prevention techniques. Just avoid using them. Just say no. Don't do the redirects and the forwards. If you do need to do the redirect and forward, try not to include user input in the forward that you do. And if you have to include user input, then you want to validate the parameter that the user is supplying. Whitelist the redirect locations. So if you are Google, or no, if you're Facebook and you want to do the redirects, make sure you whitelist it to things like Instagram that you own, right? A whitelisted domain set that does the redirection would be the idea there. Force the redirects to a page that notifies the user that the redirect is happening. This happens in a lot of sites. So if it is forcing you, if IRS is forcing you, no, if H&R Block is trying to redirect you to irs.gov, typically they would say, hey, you're going to be redirected to a site that's not H&R Block. Click here to proceed. So, yeah.
Does that all the time. You have to go to do your IRS information. It lets you know you're using the site so everybody can start process.
Oh, okay. So what is the site that does that? FAFSA. Okay.
So that's how we get our financial aid.
Oh, financial aid. Okay, so yeah, so the financial aid site is telling you directly when you're going off the financial aid site. And so you would want that to be implemented widely. Wherever you're using the location redirection, you should be implementing this kind of thing. Authorize via an access controller before doing so this relates to the forwarding. So if you're forwarding to an internal route, make sure that it hits some authorization code first before doing the forward. Okay. Here are some links to some resources for addressing this particular vulnerability. Now I'm going to briefly talk about the labs and the homework before letting you get to them. There are 5 authentication examples in Web for Pentester 2. These are relatively quick to do. So. And this will be due for Monday. So that's set from the command injection, SQL injection, and then the authorization or authentication ones will be due on Monday. So that's the only lab. In terms of the homework, you're going to do basically the lessons for these 3, and they're relatively simple. The session management challenges 1 through 6. I have some notes for each one of these levels in order to make the levels easier. So these are things that people get hung up on, so I would recommend you reading these before trying the levels on these, especially number 6. Number 6 is a real pain without this. Okay, and then the last thing is the second program. This is a timing side channel program that I referred to earlier. This is not going to be due Monday. This is going to be due a week from Monday. I just wanted to assign it now so that if you are through the labs for this time around, you'll have something to work on. This is a simpler program than the blind SQL program that's due on Monday. So on Monday, the blind SQL program and Lab Notebook 2 are due. This won't be due until the following Monday. Okay. The code lab associated with that spells out what you're trying to do pretty explicitly, so I'm not going to use class time to go over it. So with that, I'm going to allow you to get to work. Are there any questions before? 2.3 should be up. So if you go to, you might need to do a shift reload on that. So yeah, it's right here, 2.3. So that should be available. So shift reload, and then you should be able to see the 2.3.